When we think about the transistor, the tiny little building block of all modern electronics, we usually think of it as a simple switch, on or off. But that's really only half the story. It turns out this component has a completely different personality, a second face. And understanding that second face is the key to pretty much everything, from your phone's Wi-Fi to a high-end stereo system.
So on one hand, yeah, it's a nearly perfect electronic switch. But on the other hand, it can be an incredibly precise, controllable source of electrical current. So how can one little device be both of these fundamentally different things, while the secret is all in the voltages we apply to it?
So here's what we're going to do. We'll start with its familiar role as a switch. Then, we're going to stumble upon a really strange mystery that had early engineers scratching their heads. We'll solve that puzzle by looking at the physics inside the device, and when we do, we'll uncover its powerful second identity.
All right, let's dive into the transistor's first personality. This is what we see when the voltage across the device itself, what we call the drain-to-source voltage, or VDS, is really small. This zone of operation is called the triode region. What's so cool is that at these low voltages, the transistor acts like a resistor. But it's not just any resistor, it's a tunable one. It's like a dimmer switch for electricity. By changing the voltage on its gate, we can electronically dial the resistance up or down.
And it's really straightforward. You apply a high voltage to the gate, and boom, you get a low resistance path. The switch is on. You apply a low voltage, and the resistance shoots up to infinity. The switch is off. This is what makes it such an amazing electronic switch with no moving parts.
And this isn't just theory. It's happening right now, inside the device you're watching this on. Think about the Bluetooth chip in your laptop. It has one transmitter and one receiver, but only one antenna. So how does it share? With two tiny MOSFET switches. To send data, one switch flicks on, connecting the transmitter. To get data, that one flicks off, and the other one flicks on, connecting the receiver, all happening billions of times a second.
Okay, so at low voltages, it's a resistor. Got it. But what happens if we start to push it? If we start cranking up that voltage across the device? Ohm's law tells us more voltage should mean more current, right? Well, you'd think so.
So based on this resistor-like behavior, engineers came up with a simple equation. It all seemed to make sense. So put yourself in their shoes. As you turn up that VDS knob, what does your math tell you is going to happen to the current?
The theory was crystal clear. The math predicted a perfect little parabola. The current should go up, hit a peak, and then it should actually start to fall. But when they built the circuits and measured them, what they saw was completely different. The current went up, hit a peak, and then it just flatlined. It stayed perfectly constant, no matter how much more voltage they threw at it.
And this was a huge problem. As Professor Razavi puts it, it was somewhat troublesome. That's a classic understatement. It meant their basic understanding, their model, was totally wrong. They were missing something big.
So, to solve this mystery, we have to pop the hood. We have to stop looking at the simple model and start looking at what the electrons themselves are actually doing as they flow through this thing. Okay, so initially when the transistor is on, you've got this nice wide channel of electrons flowing. Think of it like a river of charge going from the source to the drain. Everything is flowing smoothly. Now, as we start cranking up the voltage on the drain side, it starts to push back against those incoming electrons. It's like we're building a dam at the end of the river. And the effect is that our river of charge starts to get narrower and shallower right at the end.
And then, at a very precise voltage, something dramatic happens. The channel shrinks all the way to zero. The river literally gets pinched off before it reaches the other side. It doesn't connect anymore.
And this pinch-off is the entire secret to the mystery. Once that channel is pinched off, it creates a bottleneck. No matter how much harder you pull with more drain voltage, you can't get any more electrons through that bottleneck. The flow has completely maxed out.
It's this weird little physical behavior that unlocks the transistor's second and maybe even more amazing personality. We've entered a whole new mode of operation called the saturation region.
So we need a brand new equation for this region. And when we work it out, we see something incredible. Look closely. The drain voltage, VDS, the very thing we've been turning up this whole time, it's just gone. It has completely vanished from the equation.
And that is the huge reveal. The current has saturated. It's hit a constant value, and it no longer depends on the voltage across the device at all. The only thing that sets the current now is the voltage on the gate, our VGS. We've created a faucet for electrical current.
This lets us simplify things beautifully. When a transistor is in saturation, we can just replace that complex symbol in our diagrams with a simple current source. And not just any current source, it's a voltage-controlled current source. We have a dial, that gate voltage, that lets us precisely set how much current flows.
So let's just put it all together right here. The MOSFET really has two faces. In the triode region, at low voltage, it's a voltage-controlled resistor, which is perfect for making electronic switches, but push that voltage higher into the saturation region, and it transforms into a voltage-controlled current source, the essential building block for amplifiers.
So why do we care so much about this? A voltage-controlled current source? What's the big deal? Well, this property is the absolute foundation for one of the most important circuits we could ever build.
As Professor Razavi hints here, a device that lets you use a small changing voltage to control a larger, steady current is the very definition of an amplifier. This is how we take a tiny signal from a microphone or an antenna and make it strong enough to drive a speaker or process data.
It's really incredible, isn't it? This single, tiny component can be both a digital switch and the core of an analog amplifier, all just by changing the voltages you apply to it. Two completely different personalities, both absolutely essential to our modern world. It really makes you wonder, what other hidden behaviors are just waiting to be discovered inside the components we use every single day?